Hi everyone, today we are going to have a look at resisted motion, vertical resisted motion with quadratic drag. So it's very similar to last time, but resistance, instead of being proportional to the velocity itself, it's going to be proportional to the square of the velocity this time. So let's get started. Obviously, there is not really that much to it compared to yesterday's in terms of the concepts. So you just wherever you see a v, you will replace with v squared, and that's it. The big differences come from the actual mathematical formulations we're gonna use. So first example, obviously upward journey. Both the gravity and resistance working the same direction, dragging you down. Yeah, and we divide everything by m to get just acceleration instead of a total force. As you can see here, it's kind of familiar, isn't it? We do exactly the same in solving this differential equation as we did previously. So we can just write dt over dv equals to a negative 1 over g plus kv squared. Okay, so you should be able to recognize that this is the best way to tackle this is integrate this into a inverse tangent function. So that's what we're going to do. So we're just gonna say, well, it is dt over dv equals to negative 1 over g squared root g squared plus root kv everything squared. Okay, because we have a function nested inside another function, so we have to we'll have to do a substitution. So if we want to integrate this with respect to dv, then we have to do the u equals to minus kv substitution, so du equals to square root of k dv. And to be able to do that substitution, we have to convert this into a k, yeah, and then multiply everything by 1 over k. So what we do now is we do the substitution, so everything should look like t equals to negative 1 over square root of k, integrating du over g squared plus u squared. So this is the inverse tangent. So we can write t equals to negative 1 over square root of k times, so it's 1 over a tan inverse x over a. So it's times 1 over square root of g tangent inverse of u over square root of g and plus c. So t equals to negative 1 over kg tan inverse. Obviously, u equals to square root of k times v, so it's square root k over g v plus c. Of course, if you want to find what c is, you just take original value where t equals to 0. We have our initial velocity v naught. So when t equals to 0, minus 1 square root of kg tan inverse square root of k g v naught plus c. Okay, which means c is obviously whatever this is, so we can just write everything down as t equals to 1 over square root of kg times tan inverse square root of kgb naught minus and tan inverse of square root of kg of v. Of course, if you really want, you can now rearrange everything and make it everything subject of, sorry, make v the subject, so we can have a function of v in terms of t. So you can do this, kg t equals to tan inverse square root of k over g v naught minus tan inverse k over gv, and then tan inverse k over gv equals to tan inverse k over gv minus square root kgt. And of course, v itself would equal to so it's it will be upside down, so it's g over k, and then tangent of tan negative 1 k over g v 0 minus k g times t. Okay, so this is something you can do, but most of the time you will not be asked to do it. All right, now let's look at this from the perspective of displacement. Once again, this is fairly straightforward. We can just divide everything by v. Sorry. dv over dy equals to negative g plus kv squared over v. So I'm sure you can see where this is all heading, because if we turn everything upside down, dy over dv equals to negative g plus correction. It's v over g plus kv squared. And with slight modification, the numerator will become the derivative of the denominator. So what do we need? So we need 2k. Yeah. So dy. So if we from here, if we just integrate both sides with respect to dv. So y just equals to, we can make the v here 2kv. So we have to 2k in the front over a g plus kv squared dv. So as you can see here, the 2kv is derivative of kv squared. So we can just keep on going from there. So y equals to negative 1 over 2k log g plus kv squared, once again, plus c. To find out what c is, obviously, when y equals to 0, we have a initial velocity, v0. So we substitute in, then obviously c equals to 1 over 2k log g plus kv squared. And of course, we can combine everything. We can just say, well, y equals to 1 over 2k log g plus kv0 squared minus log g plus kv squared. Of course, you can just write y equals to 1 over 2k log because you are subtracting two logs, you can write them as a division. So g plus kv0 squared, kv0 rather, over g plus kv squared. Alright, so this is pretty straightforward. It's more or less the same as we did previously. If you really want, you can rearrange everything and make v the subject, but it's not, you don't have to do it in this subject. Okay, so next important result with upward journey, of course, is the maximum height. Maximum height is when, obviously, when velocity equals to 0. So just imagine a particle rises up and then slows down gradually until it comes to a stop at the maximum height, and then it drops down again. So obviously, if we replace v equals to 0 into y equals to 1 over 2k g plus k v squared over g plus k v squared. If we substitute v equals to 0 into here, oh sorry, there's a log. So if we substitute z 0 into here, we end up with we just end up with y equals to 1 over 2k log g plus kv naught squared over g. Yep. So that's the maximum height can travel. So depending on what the initial velocity was, this is max height. In terms of time, how long it takes to reach the maximum height, then we can just use the time expression. So it's 1 over square root of kg, tan inverse square root of k over g v naught minus tan inverse square root of k over g v. So we substitute 0 into here, and then we just end up with t equals to 1 over kg, and tan inverse, so tan 0 equals 0, so this part goes away, and we have k over g v naught. Okay, so interesting enough, in an environment with a given k, so the given resistance, the specific resistance of the medium the object is traveling, if you have a specific k and you have a specific g, then the maximum height and the maximum time in the air is purely dependent on the initial velocity. Yeah, so in fact, if you can look at this, larger the v, the whole thing becomes larger. So higher the initial velocity, the higher the object will fly, and the longer it will stay in the air. That's pretty much it. All right, so now let's turn around and look at the downward journey. Okay, but we are still going to follow more or less the same steps, but this one is slightly more involved. So dt over dv equals to 1 over g minus k v squared. As you can see here, this expression, we don't have it on our standard integrals. But because we have subtracting a square term, so we can always treat it as a difference of two squares. So minus so square root of k v. Yeah. So how do we decompose it? So we have 1. So it's a square root of g minus square root of k v. times square root of g plus square root of k v. Obviously, we want to break it down into 2, which is g minus kv and plus b over g plus square root of kv. So that's what we are aiming at. Now, obviously, 1 would equal to a times square root of g plus k v plus b times square root of g minus kv. So let's try to figure out what b is. So if we're trying to find out what b is, then we have to make a disappear. So v has to equal to negative square root of g over k. Okay, that means 1 equals to b times square root of g minus square root, so plus square root of g over k times square root of k, which means k cancel out, so b equals to 1 over 2g, 2 square root of g. Okay, now let's do the other one. So a, we have to do the same to find out what a is. B has to disappear, so v has to equal to square root of g over k, which means 1 equals to a times square root of g plus square root of g over k times square root of k. They cancel out. So a equals to 1 over 2 square root of g as well. Okay. So here now we can expand everything. So dt over dv equals to 1 over 2 square root of g, then times one over square root of g minus square root of kv plus 1 over square root of g plus square root of kv. As you can see here, we can now change it into log functions. We can integrate this into log, so we integrate this dv, we integrate this with respect to dv, so we end up with t equals to 1 over 2 squared, g. We have to factor out negative, we need to figure out 1 out k, so 1 over square root of k, and then we end up with negative log square root of g minus square root of kv plus log square root of g plus square root of kv. And of course, because we have subtraction between two logs, we can convert them into a division. So we end up with t equals to 1 over 2 square root of gk, then times log square root of g plus square root of kv over square root of g minus square root of kv plus c. Okay, so what is c? Obviously here the c has to be this value when the v equals to 0. Sorry, no, v equals to v naught, so initial velocity. So c has to equal to negative 1 over 2 gk log times square root of g plus square root of kv naught over g minus square root of k v. V naught as well. Okay, so to combine everything, we'll end up with it's pretty messy actually. So t equals to 1 over 2 gk. We can just log g plus kv over g minus square root of kv minus log square root of g plus square root of kv naught. So I'll probably segregate these. V naught over square root of g minus square root of k v naught. Okay, so just okay, so this would be the expression of time for the downwards part of the motion. But it is often the case that your life will be made easier with the initial velocity being equal to 0, or once again something falling down from a stationary position or reaching a height then start dropping. So the velocity at the start of drop will be 0, which means the second part will, and this part will collapse, and then you just have t equals to 1 over 2 gk times we don't really need this anymore, times log g plus kv over square root of g minus kv. So this is what happens often. You will see this quite often. Okay, let's move on to the displacement. So in terms of displacement, it's very similar to what we did previously. I just keep on saying that, haven't I? Yeah, basically just dv over dy equals to g minus kv square over v, and then dy over dv equals to v over g minus kv squared. So as you can see here, we can very readily make into a log expression. So I'm just going to do that. So if we want to integrate both sides, we end up with y equals to, obviously we have to make this into negative 2k, so 1 over negative 2k log g minus kv squared plus c. Okay, so from here we can just figure out what c is. So when y equals to 0, v naught, so initial velocity, and then we can just say 0 equals to negative 1 over 2k log and g minus k v naught squared plus c. So obviously c equals to 1 over 2k log g minus kv squared 2. And then if we combine everything together, we will end up with y equals to 1 over 2k. So it will be this minus this, so it will be log g minus kv naught squared over g minus kv squared. Okay, so once again, things will probably be made easier for you by having the initial velocity equal to 0. So we end up with just y equals to 1 over 2k log g minus kv naught square over g. Yep. So this is pretty straightforward. And last bit, just like with linear drag, we're going to look at terminal velocity. Once again, because gravity and resistance work in opposite directions, so there is a specific velocity that would cancel out all the gravity. So that's when the acceleration becomes 0. So when all the forces cancel out, and then so you can just rearrange it, you will see that v equals to square root of g over k. Of course, once again, we just call it vt for terminal. All right, now let's have a look at some examples. I thought this one was quite interesting because it introduces, as you can see here, the ratio between velocity and terminal velocity. And by using this ratio, some of the math can be simplified a bit. And we'll look into that very shortly. But before that, let's just have a look at the question first. Yeah. So motion is affected by gravity and air resistance, which is proportional to the square of the speed. So obviously, once again, acceleration equals to g and kv squared, or acting in the opposite direction. So this is what we have. And next one is where we have a look at how the velocity is. So here it says the initial speed is twice the terminal velocity. So v naught equals to double vt. So first we're asked to really examine this particular expression, the ratio between the velocity and its terminal velocity, and then show that omega satisfies this particular equation. So we're going to do that. So obviously, because omega is v over vt, so v obviously is vt omega. Yep. Similarly, because vt is a constant term, so because v is simply a multiple of omega, so the time derivative of v should be the same as vt times the time derivative of omega. Yeah, because vt is just a constant term. And what is this constant term exactly? Obviously, as we saw before, vt is square root over g over k. Now, can you see what we can do now? So we can just substitute into the original equation of motion. So we have it in terms of omega and omega dot instead of v and v dot. So obviously, instead of derivative of v, we can replace this with a derivative of omega equals to 9 minus k. Instead of v, we can replace with vt omega. So vt omega squared. Sorry, t squared. Okay. What does that give us? So we have vt omega dot equals to g minus. So what is vt again? So it's g over k. So it's k times so square root. So it's g over k. And then omega squared. So obviously these two cancel out, and vt omega equals to g minus g omega squared. Okay, now what's next? Well, next thing we can do is to remember this is what we're aiming for, and we're going to use this to simplify things slightly later on. So what are we aiming for? So we end up with omega dot equals to g minus g omega squared over, what's vt again? Vt is just g over k, isn't it? So now omega dot just equals to 1, minus omega squared times g times square root of k over g. Obviously, g cancel out, so we end up with omega dot equals to, because it's asking, you see why it's done in a minute, because it's asking for a negative, so we can just factor -1 out, and we get omega squared minus 1, and then this, so we end up with square root of gk. Yeah. Now we are going to use this expression to simplify things for ourselves. So find t as a function of omega. So let's do that. Obviously, d omega over dt will have to equal to negative omega squared minus 1 times square root of gk, as what we have found out earlier. Now what we have is, once again, we solve this differential equation by dt over d omega equals to -1 over gk times 1 over omega squared minus 1. And I hope you can recognize that we have a partial fraction decomposition in our hands. So we need to find out a over omega minus 1 plus b omega plus 1 equals has to equal to 1 over omega minus 1 times omega plus 1. Because the numbers are simple, we can pretty much use the cover up rule. So a plus b omega minus 1 over omega plus 1 equals to, because we multiply both everything, so it's 1 over omega plus 1. And then it disappears, so a equals to 1 over 2, because this disappears when this part disappears when omega equals to 1, and then that's it. Similarly for b, so a times omega plus 1 over omega minus 1 plus b equals to 1 over omega minus 1. So when omega equals to minus 1, this a disappears, so omega has to be minus 1, so b equals to negative a half. Okay, now what we can do is we just substitute everything back in, so we end up with dt over d omega equals to negative 1 over gk, and equals to what do we have? So 1 over 2 omega minus 1 minus 1 over 2 omega plus 1. Of course, we can integrate now both sides with regard to omega. And what we end with t equals to negative 1. Actually, we can factor 2 out as well. gk times what is this? So it's log omega minus 1 minus log omega plus 1. Of course, we have to plus c. Alright, so to simplify everything once again, so it's just 2 square root of gk log omega minus 1 over omega plus 1 plus c. So obviously c has to be the positive, so but we don't really have to find a general expression for c, because the question asked is because we have been given initial conditions. So remember, initially at t equals to 0, yeah, v equals to 2 v equals to 2 vt. Yeah. So when t is 0, the velocity is twice the initial velocity, so the terminal velocity. So omega here is just 2. Okay, so we can substitute everything in. So t equals to so when t equals to 0, 1 over negative 1 over 2 gk log. So 2 minus 1 is 1. Omega, so 2 plus 1 is 3 plus c. Okay, so what does that give us? It means c equals to the positive this, so 1 over 2 log gk, square root of gk log 1/3. Of course, we can convert this into, we can convert log into a integer. So c equals to minus 1 over 2 square root gk log 3. Of course, we can just combine everything, and then we will end up with t equals to, actually we can make this, so t equals to, we can flip this as well. So it's 2 gk so 2 gk, 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 2 omega plus 1 over omega minus 1, because we can flip this upside down and take out the negative sign, and then minus log 3. So this is what we can do. And finally, let's look at C. Hence, find the time taken for the object to reduce speed from 2 vt to 11/10 vt. So what does that mean? So for C, it means that omega equals now 11/10 because that's the ratio. Okay, now here we can just plug all the numbers into here, and we end up with t equals to 1/2 gk times log 11/10 plus 1 divided by 11/10 minus 1 minus log 3. So t equals to 1/2 gk. What's this? So 10. So 21/10, 1/10. Okay, so it's log 21 minus log 3. So as you can see, you can divide them. So t equals to 1/2 gk log 7. So that is our solution. Now let's look at the next one. Okay. I thought this one is pretty interesting because it has both the upward and downward journeys. And it's good to go through the whole process. So firstly, let's just get these two out of the way. Equation motion of the upward and downward of journey. So obviously, upwards acceleration should equal to g, so minus g plus, let's rewrite that, equals to minus g plus, what's the resistance again? 0.02 v squared. Okay, so this is the total acceleration. Yeah, because maths is 1, so when you divide everything by 1, it stays the same. And then y for the downwards journey equals to g minus 0.02 v squared. Okay, from these two equations of motion, we're going to derive pretty much everything else we need for it. So let's look at maximum height and the time to reach that height first. So obviously for B, because we're dealing with displacement, so it should be dv over dy. And of course, the equation of the motion is exactly the same, so minus g plus 0.02 v squared. Of course, we can divide everything by v, so dv over dy equals to negative g plus 0.02 v squared over v, and dy equals to, dy over dv equals to minus v over g plus 0.02 v squared. Okay, you probably can already see it now. We're going to integrate this into a log function. Of course, we do the same to both sides. So y in the end would equal to make this, so it should be 1 negative 1 over 0.04 log g plus 0.02 v squared plus c, of course. So we can simplify this, so y equals to negative 1 over 25. Correction, 1 over 25 rather. Log g plus 0.02 v squared plus c. Of course, what we have is when y equals to 0, v equals to the initial velocity. So 0 equals to negative 25 log g plus 0.02 v squared plus c. So of course, c equals to 25 log g plus 0.02 v squared. If we combine everything, we can just say y equals to 25, because we can factor 25 out, log, because we are subtracting 2 log, we can just turn it into a division. So okay, just to make the 2 v's more different. Okay, so log g plus 0.02 v squared over g plus 0.02 v squared. Of course, at the maximum height, maximum height, v equals to 0, so y equals to 25 log g plus 0.02 v squared over g. And that is our maximum height. As you can see here, it should be a big V. Once again, all it depends on is the initial velocity and not much else. Okay, now let's look at the time it takes for it to reach the maximum height. So c dv over dt equals to negative g plus 0.02 v squared. What do we end up with? We end up with dt over dv equals to negative 1 over g plus 0.02 v squared. So here, this one, once again, we have to turn it into a inverse tangent. So if we say it's dt over dv equals to minus 1 square root of g plus square root of 0.02 times v squared. Oh, sorry, both of them. Okay, so this is a tangent, so we can write it down. Yeah, so we integrate both, and what we would end up with is t equals to, if you do all of it, you end up with 1 negative 1 over square root of 0.02 times g times tan inverse of square root of 0.02 over g v plus c. Of course, I truncated a few steps, so if you want to try to go from here to here yourselves. Okay, so what we end up with is, if that's the case, then when t equals to 0, v equals to v, exactly the same as before. We end up with c equals to 1 over square root of 0.02 g tan inverse of 0.02 over g v initial velocity. So what do we then end up with? We end up with just combine these two, so t would equal to 1 over 0.02 g, and then it's tan inverse square root of 0.02 GV minus tan inverse square root of 0.02 g times small v. Of course, at maximum height, v equals to 0, so we just end up with t equals to 1 over square root of 0.02 times g times tan inverse of square root of 0.02 over g v. So that's the expression for the maximum height, and this is the expression for the time it takes to reach there. Okay, now let's look at the downward journey. So, once again, we can treat it in terms of displacement. So dv over dy equals to g minus 0.02 v squared. V. So we divide everything by v. So dv equals to dy equals to g minus 0.02 v squared over v, and dy over dv equals to v over g minus 0.02 v squared. Unfortunately, we will have to find a way to do this. Once again, through integrating it into log. So dy, so we integrate both sides. So what we end up with is y equals to once again, so it's negative 1 over 0.04 log g minus 0.02 v squared plus c. Once again, we can simplify. Y equals to negative 25 log g minus 0.02 v squared plus c. Okay, so what is c? Here is actually not that hard to find because we have a lot of information. So when y equals to 0, because we start at from stationary. So y equals to 0. That's when the velocity equals to 0 as well, because it's starting from the rest. Sorry, the initial velocity is 0. Okay, so using that information, what we end up with is c. So y equals to 0 equals to negative 25 log g plus c. So obviously c equals to 25 log g. And then substitute it back. So y equals to 25 times log g minus log 9 minus 0, sorry, g minus 0.02 v squared. Yeah. So y equals to 25 log g over g minus 0.02 v squared. Okay, so how does this help us? Well, this is the expression for the displacement in terms of velocity. So if you look at this one, for the object to go from the maximum height and then back onto the ground, the velocity here has to make sure that the y is the same as this y, because the maximum height from the ground level to the maximum height should be the same distance as from the highest level coming down to the ground. So the previous y, so on this y and this y should equal. So we can find, that means we can find a velocity where that causes the displacement to be the same as the maximum height. So what we end up with is we should be able to recognize that 25 log g plus 0.02 v squared over g should equal to 25 log g over, sorry, this should be the initial velocity, g over g minus 0.02 v squared. Okay, obviously 25 cancel out, e, so we end up with g plus 0.02 v squared over g, sorry, v naught should be or, yeah, okay, so it equal to g over g minus 0.02 v squared, and of course we can multiply them, and we end up with g squared plus 0.02 v naught squared g minus 0.02 v squared g plus 0.02 squared v naught squared times v squared. So all of this should equal to a g squared. So obviously these two cancel out. And then what we can do is we can gather all the small v's on one side. Oh wait, sorry, negative. No, sorry, this should be a negative. Okay, so we can just turn it into 0.02 v naught to g equals to 0.02 v squared on g minus 0.02 squared v naught squared v squared. Okay, so here we can factor everything out. So 0.02 v naught squared g equals to v squared 0.02 g minus 0.02 squared v naught. Yeah, and of course we can just v squared is just this divided by so this divided by this, so v squared equals to 0.02 v squared g over 0.02 g minus 0.02 squared v naught. Of course, this cancel out, this cancel out, this cancel out. So v squared just equal to the v naught 2g over g minus 0.02 v naught. Alright, so how does this help us? Well, we can now take the square root of both sides. So v equals to, we can take this out, v naught g over, sorry, this should be plus. Okay, so sorry about that. Now what we end up with is g over g plus 0.02 v naught squared. Okay, so this provides us with an answer to the final question. So how is the size of the speed on the return compares to the initial speed? So as you can see here, the speed equals to initial speed multiplied by something. And as you may have noticed, it's g over g plus something. And because v, initial velocity, is positive, so the denominator will always be larger than the numerator, which means this number here will always be less than 1. Okay, which means v naught times a number less than 1 will be less than v naught. So it's basically saying that this v, yeah, because it's v naught times a number smaller than 1, that means that v will always be smaller than v naught, and so there is that.